there's something nice about having visual feedback, isn't there? When you can see a cart moving, it feels like you're doing something as opposed to just computing a number and getting a good score or something like that. I guess one thing I'd like to do is just give you a chance to talk about what challenges you faced and what worked for you, because we all want a little bit of intuition for how to make this thing work, or if you don't, I'm going to impose on you that now you do. So what worked and what didn't work? What metaparameters were difficult to tune? Which ones didn't matter? Stuff like that. Oh, so you ended at 0.05 and you started much higher. Okay, good to know. I didn't do any testing. I just pulled this out of my head. And my head said, that's a good number, 5%, 95%, you know, sounds good. I threw it up there. Did anybody just do 0.05 and stick with it? Oh, all these questions you can ask about your code.
That was very helpful.
Oh, good. I'm glad. That just occurred to me on a Saturday. I was sitting there thinking about my students doing their code, and I thought, I know they're going to ask me how to debug this darn thing, and I don't want them all showing up in my office, so here's what I'll probably tell them. And then I just started brainstorming on the kinds of things I do when they show up in my office. So I'm glad that was helpful. Does math still work? The last one was me just trying to be funny. This is me saying, if you got all through these questions and you're still reading, you're probably frantic and you're saying, is the universe broken? Do computers still compute properly? And then I was saying, if you're asking these questions, it's probably time to go get some help. Yeah, sorry, my sense of humor is a little on the dry side, but you'll get used to my sense of humor. Basically, when I freak out, I'm joking. All right. So one thing I made you do this time that was totally unnecessary is I gave you 2 bits of code and made you stick them together. There was the neural network in one package and the QLearner in another package. The main reason I did that was because I didn't even take the time myself to put them together. I just dumped that on you because I ran out of time prepping for the class. But as I did that, I thought to myself, hey, this will be good because it'll make sure you have a little experience wrestling with your programming language. Was that good, or was that just a waste of your time? Your poll stands up really well as long as you always start in exactly the same conditions. But if you start in some other condition and it falls over every time, what's your problem? I'm pop quizzing your intuition on this here. Yeah. So you got your code so that it works as long as you always start in the same initial starting conditions. You always start with your cart right here and the pole at a 98% angle or something like that. And who gives angles in percents? We'll say a pi halves minus 0.001 angle. Or if up is 0 degrees at a 1 degree angle. So you always start at the same place, then it recovers and balances the pole just fine. But then you start in some other condition, like the cart next to the wall and the pole leaning the other way, and you say go, and the pole just falls over, it can't handle it. What went wrong? What would you do to fix this?
You haven't explored enough of your state space.
Yeah. What's happened is your Q table is really well converged in some regions. Basically, the path that the Q agent has trod is well packed. But other places it hasn't walked before aren't so well tracked. That happens in nature, right? Where people walk, a trail forms. Where people don't walk, there's plants grow. And you can see out on the grass, wherever the university wants to grow grass, but they neglected to make a sidewalk that cuts across the diagonal, there's going to be a path of dead grass every time, right? Well, in this case, dead grass is good because it represents learning. So learning is like dead grass. We made a bad analogy today. Yeah, it does seem that way. Let me give you some empirical counters to that. So I agree, and in fact, let me make one thing clear. If you're using a Q table to store your Q values and not a neural network, absolutely, you're hosing, because let's just think about how big state space is, right? Suppose you have 10 Q values in each dimension, right? And suppose there are 20 dimensions in your problem space. What's a dimension in your problem space? It's the size of your state, right? Because we say Q is a function of your state and the actions you can choose. So if your model requires a cart velocity and a pole angle and a pole angular velocity, there's 3 values. I think we had 4, right? What's the 4th one? Cart position, yeah, okay. So we had 4 values in our state space. Suppose we were doing a humanoid robot. We'd need the angle of its elbow, the angle of its wrist, the angle of its neck, the angle of some hip joint, and 2 for each legs at least. And if it's got 10 toes, then our state space gets really big, right? And this thing's got a position, but what's the point of having a humanoid robot in a simple world? Nothing. You're going to want to have it in some complex world that's going to take another 50 variables to describe. And so now imagine your state space has, I don't know, 40 variables. So 10 to the 40th power is 10 to the 40th power. Durr. I'm a genius. Okay. Yeah, scientific notation makes that pretty dumb obvious. How many iterations of Q-learning is it going to take before 10 to the 40th power values all converge? Heck of a lot, right? I mean, we can only do, okay, what is it? 2 to the about 48-ish. We can only get about 10 to the 14 iterations done in a day of hardcore computing on a modern computing device-ish, right? So there's no way. Your Q table will never converge if you're doing that all with a Q table. If you're using a neural net, then maybe, because some parts of the space learn and then other parts generalize, and it seems to learn all over the place. One of the things we're going to be doing next, now's a good time to introduce it, is reading some papers, and this first one shows that somebody had some success with a Q-learner. So this paper is called Human Level Control Through Deep Reinforcement Learning. And some equations, and here's what they did. You ever play Atari 8600 games? Am I the only one here old enough for that? Cool. Okay. Well, back before the classic NES, yes, I'm that old, we used to play these Atari 8600 games. You have a control paddle which can move in any of 8 directions, and the button can either be up or down, or you can press the button while it's in the center. So I guess there's 9 positions, which makes a total of 18 actions, which you could do to your joystick, right? Well, they took an emulator, Atari 8600 emulator, and they stuck in cartridges, arbitrary cartridges. They were probably actually software ROMs. And they took screenshots of the screen. And this is what's cool, is nobody went through and hard-coded the state of the game. It's actually just images going in. So these images feed through this neural network, and it maps to each of those 18 actions that you can do with a video game paddle. And they just used time iterations, I don't know, whatever frame rate the Atari 8600 uses. And there's a bunch of charts about how it converged over time. And here's how it did. Now, see, there's a bunch of games here, right? Montezuma's Revenge, Private Eye, Frostbite, Asteroids, Bowling, Centipede. Any of those seem familiar to you? If you played way back in the day. Now, here's what we've got. About here is the level at which humans do, meaning they also had a bunch of humans play these games, and the AI that was trained with a Q-learner beat the humans at all of these games. And the humans beat the AI at all of these games. So apparently Montezuma's Revenge is just darn hard for a Q-learner. Based on the screenshot, it just cannot figure out which way to move the joystick. What else I think is really cool about this is they were not programming in long-term strategy or any type of, they didn't tell it how to play the game. They didn't train it. They just let the thing go and iterate for a darn long time with epsilon greedy exploration rate and screenshots and control paddles. And yet with that alone, and a great big neural net that digested the screenshots and then moved the joystick, it learned how to play quite a few games. Apparently Ms. Pac-Man's just too darn hard, so is Asteroids. That makes me sad because I used to be really good at Asteroids, and if it could win at Asteroids, I feel like that would connect with me somehow. The x-axis, we better check it out, I don't know. Percent of something. The performance of DQN, Deep Q Network, is normalized with respect to a professional human game tester. That is 100% level. Okay, so we decided that a professional human game tester, seriously, does anyone get paid to play Atari 8600 games right now? I doubt that. So I have no idea what a professional human games tester is. It must be a person who tests other games for a living, and he also knows Atari 8600 games. And you know it wasn't some guy they paid. It was probably the researcher's brother who happened to be into video games or something like that. Nevertheless, and by the way, I'm making that up. Don't go posting on social media that this paper is a scam or something, because I'm not saying that. But what I am saying is if you draw this line straight up there from 100, I guess here's where it crosses the line. No, it crosses right there. Apparently, because he's a professional, I guess regular humans can only do 76%. They probably bumped the line down a little bit to make themselves look better. Yeah, we all do that in our papers. But they're claiming around here somewhere is where it starts being as good as a human. Video pinball, boxing, and breakout, it just kicked trash at. And so I've never heard of most of these games. Ooh, James Bond, I recognize that one. Tennis, Pong, Space Invaders. Hey, there you go.
I was reading a paper